Welcome back to AI Unraveled, the podcast that cuts through the hype to deliver zero noise, high signal intelligence on the world of artificial intelligence. Today, we're stepping into the most personal frontier of AI innovation, human health. In this special episode, Decoding Your Health Story, how Google's AI is revolutionizing diagnosis, genetics, and personalized care. We explore how massive biobanks are collecting data from millions and how AI is becoming the key to unlock it. We'll look at new research from Google that uses AI to predict health traits from imaging, improve the discovery of individual genetic variants, and combine genetics with health data to give us a complete picture of health and disease. But before we dive into the data, a quick word for the leaders listening. Stop marketing to the masses. Start briefing the C-suite. You've experienced the power of AI Unraveled, zero noise, high signal intelligence for the world's most critical AI builders. Now leverage our proven methodology to own the conversation in your industry. We create tailored, proprietary podcasts designed exclusively to brief your executives and your most valuable clients. Stop wasting marketing spend on generic content. Start delivering must-listen, strategic intelligence directly to the C-suite. Ready to define your domain? Secure your strategic podcast consultation now. The link is in the show notes. Stay with us and let's explore how AI helps decode the human health story.
So what if cutting-edge AI could help decode, your unique health story? Everything from a single X-ray right down to the subtleties hidden in your genetic code. Imagine a shortcut to being truly well-informed about where medicine is heading.
That's a powerful image. And it's actually becoming less science fiction and more reality.
Right. So today we're taking a deep dive into some really groundbreaking advancements in medical AI. Specifically stuff coming out of Google research and DeepMind.
Yeah, some fascinating work.
Our mission really is to unpack how these new multimodal AI models are changing the game, how they understand and interact with all sorts of different medical data.
We're talking imaging, genomics, a whole spectrum.
Exactly, and the promise is, more personalized health insights, maybe faster, more accurate diagnoses for you.
That's the goal. We'll be looking at insights from several key papers today. There's the one on MedGemini, another on multimodal LLMs for individual health data.
Right, and also DeepNull, MRE-SEL for genetic analysis, that IH retinal clock paper, and one on variational inference for polygenic risk scores. Quite a list.
It is. Lots to cover. But it paints a really interesting picture of where things are going.
Okay, let's unpack this.
It's genuinely exciting to see how these models are pushing boundaries. The core idea, really, is moving beyond just looking at one type of data in isolation. Instead, it's about integrating information from, multiple sources all at once.
Kind of like how a doctor looks at your test results, your symptoms, your history, and everything together.
Precisely. Exactly like that. But doing it on a scale and with a depth that's just unprecedented.
That holistic approach, it sounds incredibly powerful. And you mentioned MedGemini is kind of at the forefront here.
Yeah, MedGemini is a really key development.
Okay, so what is it exactly? What makes it such a big step?
Okay, so MedGemini is basically a new family of AI models. They're built on the core capabilities of Google's Gemini, which is already multimodal, meaning it handles different data types. But MedGemini has been specifically optimized, fine-tuned, really, for medical use.
So it's like a Gemini that went to med school.
Something like that. Think of it as a generalist medical AI. It's designed to understand really specialized medical data, stuff you just wouldn't find in a general-purpose AI like ChatGPT or even the standard Gemini.
Okay, so it knows about X-rays and genes, not just cats and poems.
Exactly. It's a leap towards a more comprehensive AI in healthcare, one that can handle everything from images to genomic sequences.
That's a fascinating concept, though, a generalist AI that's also a deep medical specialist. How does it actually learn all that specialized stuff? It must be quite a process.
Oh, it is. It learns through fine-tuning, basically training it further on an enormous, incredibly diverse set of medical data.
Like what kind of data?
We're talking 2D and 3D radiology scans, like chest X-rays, CT scans. Then there's histopathology, which is tissue samples under a microscope, ophthalmology, eye scans, dermatology, skin images, and even complex genomic data. And what's really innovative, I think, is how it handles 3D data, like those CT volumes.
Yeah, you mentioned that was tricky.
Right. So it cleverly uses Gemini's existing video understanding capabilities. It processes the multiple 2D slices of a CT scan, almost like frames in a video, capturing that depth dimension.
That's really smart, treating a stack of images like a movie clip.
It is. And all this training, it happens on these massive Google TPU-V4 accelerator pods,
Yeah.
serious AI supercomputers. It shows the kind of computational power needed for these breakthroughs.
Right, not something you run on your laptop. So, okay, it's trained on all this data using clever tricks. What are the results like? What can it actually do,
Yeah.
especially in areas like radiology? Getting those reports right is crucial.
Absolutely. And in radiology, MedGemini 2D, the one focused on 2D images, is really setting a new standard for AI-generated chest X-ray reports.
How good are we talking?
Well, expert radiologists evaluated the AI reports. On two different data sets, they found that for normal cases, something like 57% and 96% of the AI reports were equivalent or better than the original human reports.
96% on one set. Wow. And for abnormal cases.
Still impressive. 43% and 65% on those same two data sets were rated equivalent or better. That's a huge step towards having AI reliably assist radiologists, maybe handling initial reads or simpler cases.
Okay, that is significant progress. What about the 3D scans, the CTs?
So MedGemini 3D is actually the first ever large multimodal model to generate reports for 3D CT volumes. That's a milestone in itself.
And the quality.
About 53% of its AI reports were considered clinically acceptable. So very promising, definitely, but it also shows there's still work to do to fully match, expert human quality in that really complex 3D space. Further research needed for sure.
Makes sense. 3D is inherently more complex. So beyond just writing the full reports, what else can MedGemini do with these images? Can it, answer specific questions about what it sees?
Oh, absolutely. Visual question answering, or VQA, is another key area. MedGemini 2D actually surpassed the previous best performance on chest X-ray VQA tasks.
So you could ask it, is there evidence of pneumonia? And it could answer based on the image?
Essentially, yes. And it also performs really well in general radiology VQA and just classifying images. It actually exceeded the state-of-the-art or previous baselines on 17 out of 20 different tasks they tested it on.
17 out of 20, that's pretty dominant. Does this apply to other image types too, like the skin photos or tissue samples?
It does. Its ability to generalize is, frankly, remarkable. It surpassed the baselines in histopathology, ophthalmology, and dermatology image classification across 18 out of 20 tasks in those areas, too.
Wow.
And it's getting close to the performance of models that were specifically built just for those single tasks, which is kind of the point of a powerful generalist model.
Right, one model doing the job of many specialized ones. Okay, that's the imaging side. What about genomics? Predicting disease risk from genes that feels like a totally different beast.
It is a different beast, yeah. But MedGemini has a component for that, too, called MedGemini Polygenic. And it actually outperforms the standard linear methods we typically use for polygenic risk scores, or PRS.
Okay, better risk scores. But you mentioned something even more fascinating earlier.
Yes. Get this.
Mm-hmm.
It even generalizes its predictions to genetically correlated diseases it was never explicitly trained on.
Wait, how does that work?
Well, it seems to learn deeper underlying biological connections. So if it's trained to predict risk for, say, heart disease, and another condition shares some genetic risk factors, it might also show some predictive ability for that second condition, too, even without specific training data for it.
That's incredible. It implies it's learning something fundamental about the genetics.
Exactly. It's a big step towards understanding your broader genetic predispositions, maybe for a whole family of related conditions.
Just think about that for a second. Getting an X-ray result back in minutes, potentially, not days, or starting to understand your genetic risks years before anything might show up. That's the kind of immediate life-changing potential MedGemini seems to be unlocking for you, the patient. Which brings us nicely to our next section, really diving deeper into those genetic insights with AI. Understanding complex traits, it's often not just about one gene, right? It's how genes interact with other things.
Absolutely. Things like your diet, your lifestyle, your age, other environmental factors. We call these covariates in genetics. And their effects, especially how they interact with genes, can be really complicated, often nonlinear.
Nonlinear meaning, not just a simple more of X means more of Y relationship.
Exactly. It could be thresholds or complex curves or interactions where the effect of a gene changes depending on your age, for example.
Yeah.
And traditional genetic studies, like genome-wide association studies or GWAs, often struggle with this.
Why is that?
Because specifying the exact mathematical model for these complex nonlinear interactions beforehand is incredibly difficult, maybe impossible sometimes. And that's where new methods like deep null are coming in.
Okay, deep null. Tell us about that. How does it help unmask these hidden genetic signals when the usual tools kind of fall short?
So deep null uses a deep neural network, an advanced AI learning system specifically to identify and then adjust for those nonlinear and interactive effects from covariates within a GWIs.
So it learns the complexity directly from the data instead of us having to guess the right formula.
That's the core idea. And the impact is pretty significant. It manages to maintain control of false positives, so it's not just finding random noise while actually boosting the statistical power to find real genetic associations when those nonlinear effects are present.
And if the effects are simple and linear, does it mess things up?
That's the beauty of it. No,
Okay.
it incurs no power loss in those simpler linear scenarios. So it intelligently adapts. It only brings out the big guns when needed, you can say.
That sounds like a major improvement. Have we seen specific results? Like, has it actually found new genetic links?
Yes, definitely. In analyses across 10 different traits or phenotypes from the UK Biobank, things like LDL cholesterol, ApoB levels, even glaucoma referral probability, Deep Null discovered, on average, 6% more genetic hits.
Hits meaning specific genetic markers linked to the trait.
Exactly. And about 7% more loci, which are the specific locations on the genome where those hits occur. Plus, it also improved the prediction of the phenotype itself, based on genetics and covariates, by an average of 23%.
23% improvement in prediction. That's substantial. It really makes you wonder, doesn't it? If we can properly account for these complex interactions, how much more is hidden in our genes that we just haven't been able to see clearly before?
The critical question. It suggests we might be underestimating the genetic contribution to some diseases because our tools weren't quite sharp enough.
Okay, so that's handling complexity within traditional GWIs. But what about bringing in other kinds of health data alongside the genetics? The stuff we generate constantly now, ECGs, data from smartwatches. How can AI help integrate all of that?
Right, that leads us to MRE-GLE. This method takes on the challenge of integrating multiple types of what we call high-dimensional clinical data, or HDCD.
High-dimensional meaning complex data streams, not just simple numbers.
Exactly. Think detailed ECG waveforms from a hospital 12-lead machine, or the PPG waveforms, that's the light-based heart rate sensing from your smartwatch. MRE-GLE is designed to use these kinds of rich data sources in genetic studies.
Okay, how does it work? How does it combine, say, an ECG signal with genetic information?
It uses another advanced AI technique, this time a convolutional variational autoencoder. Bit of a mouthful, I know.
Yeah.
But think of it like a smart compression tool. It learns to take these complex inputs, like the squiggly lines of an ECG, and represent them in a much simpler, lower dimensional form while keeping the important information.
Like summarizing the key features of the heart rhythm.
Precisely. And once it has these compressed representations from potentially multiple data sources like ECG and PPG, it can then combine the GWA's results derived from these representations. It lets you leverage signals from different modalities together.
That makes a lot of sense, getting a fuller picture by combining signals. What kind of impact has this had, say, for cardiovascular health?
The impact is significant. MRE-RGL showed real advantages over unimodal methods that just look at one data type at a time. For instance, using a detailed 12-lead ECG dataset, it identified nearly 20% more genetic loci associated with ECG features.
Wow, 20% more.
And even when combining a simpler single-lead ECG with smartwatch PPG data, it still found 13% more loci. And crucially, the genetic risk score it generates significantly outperforms scores based on single data types when it comes to predicting actual cardiac conditions, like atrial fibrillation or AFib.
So better prediction of things like AFib by combining these different heart signals with genetics. That's a clear win for potential early detection or prevention.
Absolutely. It shows the power of integrating these rich, high-dimensional data streams that we're collecting more and more.
So we're finding more genetic hits, more loci basically, getting more precise markers for disease risk, thanks to AI integrating all these different data streams. Now, speaking of precision, let's talk about refining those polygenic risk scores themselves. There's another method called BBVIPRS.
Right, BVIPRS. That stands for Black Box Variational Inference for Polygenic Risk Scores. It's another approach aimed at constructing more accurate PRS directly from the summary statistics you get out of a GWS.
And PRS, just to remind listeners, that's the score summarizing risk based on potentially thousands of small genetic effects, right? Like a genetic report card.
Exactly. A single number summarizing your overall genetic predisposition for a trait or disease. Now, BBVRS, performance-wise, it's generally competitive with other leading methods.
Okay, competitive is good, but does it excel anywhere specific?
Yes, it significantly outperforms a well-known standard method called LDPRED2 in certain specific scenarios, particularly when the overall heritability of trait is low. meaning genetics only explains a small part of the variation, but the fraction of genetic variants that are actually causal is high.
Okay, low heritability but many contributing genes. That sounds like a tricky situation to model accurately.
It can be. And in some simulations reflecting that kind of scenario, BBA-PRS showed an absolutely massive improvement, something like an 80% gain in predictive power compared to LD-bred 2.
80%? That's huge in specific contexts.
It is. It suggests that for certain types of genetic architectures, this method might offer a real advantage in building more accurate risk scores.
So, pulling this genetic section together, what does all this mean for you, listening right now?
It really means AI is sharpening our tools. It's refining our understanding of how your unique genetic blueprint contributes to your health risks. And that ultimately paves the way for potentially much more precise, more personalized preventative strategies, tailored just for you. Exactly. Moving beyond one-size-fits-all recommendations.
Which leads us beautifully into our third section, AI for really personalized health, and maybe even discovering new kinds of biomarkers. Let's start with HELM. What's that about?
HELM stands for Health Large Language Model for Multimodal Understanding. It's essentially a framework designed to empower large language models, like the ones driving chatbots, to truly understand diverse, individual-specific health data.
So taking the power of LLMs, but grounding them in actual complex health information about a person.
Precisely. It's a crucial step towards generating personalized health insights that go way beyond what a generic AI could possibly do. It's about understanding you.
Okay, how does it achieve that? How does it get an LLM to understand, say, lung function tests alongside lab results? That multimodal understanding seems key.
It is key. HEL does this by encoding complex data types directly into the LM's language. It translates things like time series, spirogram curves, those graphs showing how you breathe from a lung function test, and also standard tabular clinical data, age, sex, BMI, lab values. It translates all of that into the LLM's token embedding space. Think of it as creating a common AI vocabulary where all these different pieces of health information can coexist and be understood together.
So the AI can see the connections, like how your lung function might relate to your age and BMI and recent lab results.
Exactly. It allows the model to process and reason over this rich, multifaceted picture of an individual's health simultaneously.
That's a massive leap from just feeding it text or maybe one type of data. How well does it actually perform? Can it predict diseases better by combining info this way?
The results are really promising. For example, in predicting asthma, HELM achieved an AROC of 0.75 when it combined the tabular data with the spirogram curves.
And AROC, that's a measure of how well it distinguishes between people with and without the condition, right? Higher is better.
Right, and that 0.75 is a really significant jump from only 0.49 when it just used the tabular data alone. It clearly shows the power of integrating that complex time series lung function data.
That's a huge difference. Does it work well for other conditions too?
Generally, yes. Across 8 common conditions, they tested things like diabetes, hypertension, stroke, HELM, often matched or even outperformed traditional machine learning models designed specifically for those prediction tasks.
Okay, here's where it gets really interesting for me. Imagine an AI that doesn't just predict risk based on numbers, but truly understands your individual health profile as this rich, complex story, and then uses that understanding to give you personalized advice. Can Helm do that?
It's heading in that direction. Helm can actually power personalized health conversations. For instance, the research showed it could provide different, tailored exercise recommendations based on a person's predicted asthma risk, drawing on their specific data profile.
So not just generic advice, but advice adapted to your specific situation as understood by the AI.
Exactly. It's moving towards a much more interactive, nuanced, and genuinely personalized health experience, almost like having a super-informed personal health advisor available.
That feels like a glimpse into the future of managing chronic conditions, maybe. Now, finally, let's talk about eye age, this idea of a retinal aging clock. What is this?
iAge is a deep learning model that was trained to predict a person's chronological age, their actual age in years, based only on a retinal fundus image. That's the photo taken of the back of your eye during an eye exam.
Predicting age just from an eye picture, how accurate can that possibly be?
Remarkably accurate, actually. On one large data set, it had a mean absolute error of just 2.86 years. On another, it was 3.3 years. That's significantly better than other aging clocks based on different types of biological data.
Wow, within about 3 years just from looking at the retina. Okay, so it predicts your eye age. Then what?
Then the model computes something called iAge Excel, iAge acceleration. That's simply the difference between the age predicted by the model, your eye age, in your actual chronological age.
So if the model thinks your retina looks older than you are, you have positive acceleration, and younger, negative.
Exactly. And this IHXL turned out to be really significant for understanding biological aging, maybe even more than chronological age.
How so? What does it tell us that just knowing someone's age doesn't? Or even other biological age tests?
Well, the fascinating finding was that this IHXL was highly independent of other common measures of biological age, like phenotypic age, which is often calculated from blood test results.
So the eye is reflecting something different about aging than the blood is.
It seems so. And crucially, even when they accounted for phenotypic age in their analyses, having a higher eye age excel, your eye looking older than your age, was still a significant predictor of all-cause mortality. It had a hazard ratio of 1.026 per year of acceleration.
Whoa. So even if your blood work looks fine for your age, if your retina looks older, that independently predicts a higher risk of dying.
That's what the data suggests. It implies eye age is capturing a distinct and potentially very valuable aspect of the overall biological aging process, a piece of the puzzle that other markers might be missing. It's a new window into our systemic health.
That's incredibly powerful. What about tracking changes over time? Can it see if someone's eye aging is speeding up or slowing down?
Yes, it can. When they had longitudinal data, multiple eye scans from the same person, over time, the models could predict individual aging trajectories, even within timescales of less than a year, with about 71% accuracy.
Detecting aging changes in under a year from eye scans, that's pretty sensitive.
It is. And
Yeah.
there was even a cool biological validation. The researchers identified a gene linked to eye age through GWs. They then found the equivalent gene in fruit flies. And when they knocked down its activity,
Meaning they reduced its function.
right, when they did that, it actually slowed down the age-related decline in the fly's vision.
Wow. So manipulating a gene linked to the human eye age score affected aging in flies. That's strong biological evidence.
It really is. It strongly suggests that retinal health isn't just about vision. It can be a powerful indicator of overall health and the aging process throughout the body. And because eye imaging is relatively cheap, non-invasive, and common, eye age looks incredibly promising for broad longitudinal health monitoring, maybe part of regular checkups in the future.
Amazing. Okay, so let's try and synthesize this deep dive a bit. We've covered a lot of ground.
We've seen how AI is moving forward on multiple fronts, from these broad, generalist models like MedGemini that can tackle many tasks,
Right, the reporting, the Q&A, the genomics.
to more specialized models like DeepNull for uncovering hidden genetic signals, MRegiLE for integrating different clinical data streams, HelloMM for personalizing LLM interactions with your health data, and IH for finding entirely new biomarkers in unexpected places, like the eye.
And the common thread seems to be tackling complexity, right? Handling diverse, messy, real-world medical data in ways we couldn't before.
Exactly. This isn't just about doing things faster. It's about achieving greater depth, more precision, and ultimately more personalization in how we understand health and disease.
It's truly remarkable how these models are being designed specifically to handle that messy reality. You know, the 2D and 3D images, the huge genomic sequences, those complex time series signals from monitors or wearables. Integrating all that is the real game changer.
I agree. That integration is key.
So the why it matters for you, the listener, it really comes down to a few key potential benefits, doesn't it?
I think so. First, potentially faster, more accurate diagnostics. Getting those initial reads on X-rays or CT reports much quicker, perhaps more reliably.
Second, a deeper understanding of your own personal genetic predispositions and risk factors, thanks to methods like DeepNull and better PRS.
Third, the real possibility of truly personalized health recommendations and proactive interventions. Advice tailored to your unique data profile, powered by models like Helm.
And fourth, this exciting prospect of new, non-invasive, maybe low-cost biomarkers, like your eye scan revealing profound insights into your aging process and overall health, thanks to things like eye age.
Those are the big promises, definitely.
Now, while this is all incredibly promising, we should also add a note of caution, right? Medicine is safety critical.
Absolutely crucial point. These technologies, especially the ones generating reports or giving advice, are still largely in development. They need much more rigorous testing, validation, and careful evaluation before widespread, routine clinical use. Safety has to be paramount.
And the data itself, bias is always a concern with AI, isn't it? Ensuring these models work fairly for everyone.
Indeed. The potential for data bias, whether based on demographics, population studied, or even data quality and also data contamination during training, These require constant vigilance and specific mitigation strategies as these models are developed and deployed. We always need to be asking, who does this work well for? And are there groups it might miss or misinterpret? There's always more to learn and refine.
Definitely. Okay, so we've explored how this wave of multimodal AI is really pushing the boundaries, unlocking new layers of insight from pretty much every type of health data imaginable.
That's a fascinating time.
It really is. So, here's a final provocative thought to leave you with. As these AI models continue to learn, as they synthesize more and more information from every corner of your health profile, your genes, your scans, your wearables, your clinical history, how might your relationship with your own health, your own well-being fundamentally change?
Hmm.
Will knowing your personalized risks and insights with this new level of clarity empower you, maybe encourage you, to take an even more active, informed role in shaping your own health future?
It's a profound question. Does more information automatically lead to better action? Or does it require a new way of interacting with that information?
Right. It truly makes you think about the incredible potential, but also maybe the new responsibilities that come with these tools for potentially a much healthier tomorrow for all of us.
That was a look inside the groundbreaking work from Google Research, demonstrating how AI is not just assisting doctors, but fundamentally changing how we understand our own genetics and health biology. The scale and speed at which AI can analyze this data means a new era of preventative medicine and personalized care is already upon us. Thank you for tuning in to this special episode of AI Unraveled. If you found the intelligence in this episode valuable, please do us a quick favor. Like and subscribe to the podcast on your favorite platform. It's the best way to ensure you never miss our next deep dive. And for our business leaders, if you are ready to stop broadcasting and start briefing your most valuable clients and C-suite, find the link for a strategic podcast consultation in the show notes. Until next time, keep unraveling the future of AI.